Early in my junior year, my dad gave me a clipping about Caltech. He said, I want you to apply there. I want to make sure there's at least one school where you don't get in. I said, okay, thanks, Dad, I'll do it. I don't know how or why, but Caltech did let me in. Hi, I'm Julie Cornfield. I always go by Julie, but you'll see my legal name is Julia Ann Cornfield. And I'm a professor of chemical engineering here at Caltech. When I arrived on campus, it was a bit strange. It was 1979, and there were so few women. There were always like hydration spheres of men around each woman student. So I'd never sung before, but I joined the Glee Club. It was a really lovely opportunity to just be surrounded by women for a few hours every week. And the same thing with women's soccer, you know. But the experience of being at Caltech was really special. One of the things I remember, I was in a recitation section for physics, and it's being run by Max Delbruck, who's a Nobel laureate and one of the creators of biophysics. He was so intimidating, really. He'd ask you a question and you pick up your notes to go to the board, put your notes down, you know? But he was also really, really sweet and very devoted. So that year he was dying. And what did he choose to do in his final year? Be a freshman TA. So one day I'm walking up the steps and I said, Professor Delbruck, how are you feeling today? And he said, oh, I had a transfusion yesterday. I feel like a tiger. Here's this person, he's dying. He wants to interact with freshmen. And after a transfusion, he feels like a tiger. You know, I mean, you can't match that. You can't match it any which way at all. It's just amazing people and just being able to be with them. You know, it's a really inspiring experience. Yeah. So as an undergrad, I loved statistical thermodynamics much more than, you know, conventional thermodynamics. I just so enjoyed thinking about these molecules, each one as like a statistical mechanical experiment, each one, you know, and they're everywhere, right? So you look at your carpet, you look at what you're wearing, you look at what you're made of, you know, it's all polymers, right? And thinking about how they move and how we can use the way they move to achieve new things. It just keeps becoming new again. Each wave of discoveries opens up a vista of what we don't know. And it's a very active process. Between the people and the problems always being renewed, it's really exciting. I have a grad student, Priya Chatur, who taught me about the existence of bacterial films that look like opals. And then she said, and Jared Ledbetter here at Caltech knows about it. I'm like, well, let's get together with Jared Ledbetter, you know? And so we start learning about these biofilms, and he told us where to go on the ocean to take samples. And so Priya's growing up living opals. It's just the things that the students create and the students teach you. That is absolutely my favorite thing. Feeling like I get to be here for this, you know, that's so great. Usually we don't really appreciate what a miracle it is to have the fall of each academic year. You know, that's definitely a silver lining from the pandemic is, you know, once in your lifetime to really feel like how lucky we are just to be able to be together and study together, yeah. Hello, thanks so much for joining us for this lecture. I wish we could be together in person, and I encourage you to communicate with me throughout the lecture using the chat feature, and we'll collect your questions and I'll be able to answer them at the end. So as soon as you have a question or a comment, a suggestion even, please go ahead and type it in. I guess that can be one of the silver linings of being remote. The story I want to tell you has a kernel of science, but a lot of people and a lot of character and personality. And I'm going to focus on 4 people who I admire very much, and I feel very grateful for having had the opportunity to work with them. So Amari David, Jeremy Wei, Virendra Sarohia, and Hojin Kim. And the circumstances that brought us together dealt with disasters that happened far apart on the world and far apart in time. And it's, to me, an inspiring story of how people from all over the world can come together and tackle a problem together. The first disaster that I'll talk about going around the world is in Afghanistan. So during the war, you may have read stories about IEDs, and in particular, the explosive being detonated right under the fuel tank, which maximized the injuries to US warfighters, and also the injuries were quite horrible. And so it was a very strong motivation to try and come up with technology that would protect them. The second example as we go around the world is from Tenerife. It's an island in the Canary Islands, and just off the coast of Africa. It's a beautiful place, and people go there to relax and enjoy. But in 1977, there was an impact on the runway in very dense fog, in which one plane was trying to take off, and due to a miscommunication with the tower, they struck another plane that was taxiing out of their way. Then the most troublesome, the most painful was in New York City in 2001, which claimed the lives of over 2,800 people. And those far-flung disasters ended up bringing us together from around the world. So I grew up in the San Francisco Bay Area, and Amaury spent most of his childhood in Tahiti growing up. And South Korea is the home for Ho-Jin Kim. So he's going to come in late in our story. And then Ming-Sin Jeremy Wei from Taiwan. And there you see Taiwan. And from an area of India in the very far north, Punjab, is where Virendra Sorohia went to school. And it's interesting that all of us converged on Pasadena. So how did that happen? So the confluence of the various disasters and the technology that might remedy it is what got us all together in Pasadena. So in 2001, both Virendra and I were in Pasadena. And although we were similarly disturbed at the initial course of events after the Twin Towers collapsed, the haunting effect it had on Virendra was even more profound than anyone else I knew. And so he was working at JPL, the Jet Propulsion Laboratory, where he'd been working since he graduated with his PhD from Caltech in 1975. And I was working on the Caltech campus. He came to me in 2002 with a problem that seemed very far from my current expertise. And so what was I thinking about when he came to me? Well, the kind of molecules I was thinking about were polymers, long chain molecules. I was worried about how they crystallize. I was thinking about how they stick together. I was wondering about their shape when you give them a complicated architecture, wondering about how they phase separate. So what is this word polymers? What is this about? So the root of the word comes from poly, meaning many, and meros, meaning parts, many parts. And so that naturally leads to the question, how many is many? So you're probably familiar with water molecules having 2 hydrogens and an oxygen. Something like propylene glycol, an additive in cosmetics and foods. It's got 3 carbons as well as some hydrogens and oxygens. And then you might think of like biological molecules, what we're made of. So here's an example of a relatively small biological polymer. It's a growth factor. It has 67 repeat units. And you look at that and you might say, oh, that's kind of a big molecule. Well, the molecules I'm going to talk to you about today have more than 1,000 repeat units. In fact, the ones that are the most interesting have more than 10,000 repeat units. So what do they look like next to this molecule? So if this was the growth factor, this is what our molecules would look like. They have tens of thousands of units. At each unit, they can take lots of different conformations, and so they adopt a configuration at any one moment that's a random walk. This is 3 different random walks. And you can imagine there's millions and millions of millions more. So it's hard to kind of draw one. So when you see this cartoon with a little squiggly line, this is what I'm trying to capture, but it's hard to draw. And then what's really special about these is that they can stretch enormously. So here's those same 3 random walks. And their size for something that has 10,000 repeat units is only 1% of their fully extended length. And that is why Virendra came to see me in 2002. So if you imagine something familiar, a rubber band, and you think about, why can I stretch this so much without it breaking? It's the fact that these molecules, well, then I broke it. So it's the fact that these molecules can deform without breaking any bonds, and then collectively withdraw back. And that's one of the key attributes for the work that we did together on trying to make fuel safer. So he came to me in 2002 because of a disaster in 1977. He got his PhD in 1975, so he was a young man at the time. And the accident happened on the largest of the Canary Islands, Tenerife. And as I mentioned, there were 2 jumbo jets, a KLM jet taking off, and a Pan Am jet trying to taxi out of the way. The Pan Am jet actually had most of its passengers who embarked in Los Angeles. It also landed in New York for fuel, but it only picked up a few passengers there. So it had a pretty profound effect on the United States and California in particular. Of the people who were on the 2 planes, everyone on the KLM plane died. And the vast majority of the people on the Pan Am jet died. And this was heartbreaking because it happened on the ground, right? It seems completely avoidable that people should have been able to walk away. But the problem was the fuel fire. So Virendra got working on a binational US-UK project dedicated to trying to make it impossible to form a mist like the mist that happened on this collision, and therefore mitigate the possibility of this extremely hot fire that claimed the lives of the people on board the 2 planes. So what happened in the wake of that disaster? So the fuel, so both planes were completely loaded with fuel, and of particular significance, the KLM jet, when it hit the ground, so part of its structure was torn away, it became unstable, it crashed, about the length of a football field away from where the collision occurred. And its fuel was dispersed into a fine mist, mixed with air. So it was an explosive mixture. And in the case of an accident like that, you always have sparks coming from metal grinding against metal, metal on pavement, hot engines. So you always have ignition sources present. And Virendra taught me, when the mist forms small droplets, much smaller than the width of a human hair, they release vapor relatively quickly because they have so much surface area. That means that when it does ignite, the flame front propagates quickly and releases a lot of heat, which causes all the rest of the droplets to evaporate. And so you end up with a large self-supporting fireball, which can also heat up the fuel that has spilled in the area and quickly cause it to all be involved in fire. So what was his project? He was working with this large binational team with researchers from NASA and FAA and their counterparts in the UK, developing a fuel additive that would interfere with the way that the drops break up in the event of a crash. So they could shift the, let me turn on this nice pointer here. They could shift the drop size from being small compared to the width of a human hair to being about the width of a human hair. When Virendra taught me that that makes a big difference, I could not believe him, but I'll show you evidence that you can see for yourselves. That if you shift the drop size distribution, much less vapor is produced in a given amount of time. So while the igneous sources are present, they can ignite that vapor, consume it, and the rest falls down like rain. And so you end up with a small, self-quenching, relatively cool fire, which delays the ignition of any spilled fuel as well, giving firefighters a chance to control the fire and allow people to just walk away. So the effect that they were using is like the effect of a rubber band, but on a molecular scale. They were dissolving molecules in the fuel that when they stretch, they resist the elongation of the filaments of liquid. And so instead of forming a fine mist, so on this side of this picture, you see water with no long chain polymer added. And you can see that it's forming drops that are so fine that to your eye, you can't even pick them up. It just looks like a cloud. On this side, you have water with a little bit of polymer added, and the polymer is quite long, so that when these filaments start elongating and getting ready to break up into drops, the polymer says, no, you don't, and it keeps the filament wide, and then it has time to break up before it gets very fine. And so the droplets, as you can see, are much bigger. And that is the key effect that they were using to try and make fuel safer. And they had some tremendous successes. So they were working with a polymer that had been developed by a British company, ICI, Imperial Chemical Industries. And they were adding it at a low concentration to jet fuel. Here's an experiment they did with surplus military aircraft. So these were already, kind of in the recycle bin of aircraft. And they dragged them down a sled to have a controlled impact. So they would impact the same way with the same obstacles. And you can see the dramatic difference in the way that the fire behaves when you have jet fuel with no polymer compared to jet fuel with this ICI polymer called FM9. So if you hear me saying FM9, it's referring to this polymer that was contributed by the UK side of this collaboration under conditions that no other polymer be tested. So that'll come back in 2002. This is a remarkable achievement. If you look at the mist that forms here, again, these drops are like the width of a human hair, whereas these that burned into this incredibly hot fireball, they are 5 to 10 microns. They're 10 times smaller. So it still looks like a mist, but even though they confirmed that the fire got started, the fire extinguished itself and the drops settled to the ground. Now, this research abruptly stopped in 1985 due to a full-scale demonstration that was performed here in California at Edwards Air Force Base. The team was so confident, based on seeing results like these, that they invited the media to come to the controlled impact demonstration. And in that demonstration, they only had one aircraft. It was 727, I believe, a passenger aircraft outfitted with crash test dummies, all kinds of measurement devices. And they were bringing it in a remote-controlled landing when doing remote control was fairly new. So as it was coming into the runway, it didn't align properly with the barriers that were intended to simulate what would happen in a crash. And instead, a barrier ended up going right through one of the engines. It created the appearance of a huge fireball. And so click, click, click go all the cameras, and front page news all over the world. What a ridiculous failure this is. So Virendra's boss tells him, just keep your head low and we'll work on something else. And he said, if I hadn't been 20-something and that young, I would have fought back because the test was a success. And I'm like, come on, Virendra, I was reading newspapers in 1984. It was not a success. He said, I'll go back into my files and I will bring you evidence. And so he brought evidence that the paint was intact on the fuselage, whereas in a test like this, the aluminum has melted before the plane comes to rest. So by and by, he was able to persuade me that this idea really had merit. But they'd stopped working on it in 1985. So in 2001, it wasn't in the fuel. And Virendra, his daughter, asked him, "Dad, why wasn't your polymer in the fuel?" And he took that really seriously. He came to see me 6 months after the event, and he still looked as sick as everybody felt on the first day. So he kept telling me, we should have kept working on the polymer. We should have kept working on the polymer. ICI wouldn't let us change the polymer. And by, he persuaded me that there was some hope, that we really should work on the polymer. And as an engineer, one of the gifts he gave us was to tell us what were the unmet criteria at the time when they stopped working on it. The polymer has to be effective at low concentration. It has to be resistant to non-intentional degradation. So if you're pumping it through a pipeline, it can't break. If you send it through a filter, it can't break. Their polymers all broke. I'll tell you more about that. It has to be soluble over a wide temperature range. It has to be compatible with getting particles and water droplets out of the fuel. It has to atomize going into the engine. They were going to have to retrofit every single plane to get this polymer degraded before it goes into the engine. And it has to burn cleanly. So that's what we set out to do. And in 2003, we started working together. And our initial idea was picking up on a lead in the prior literature, which had suggested using supramolecular polymers. So what does supramolecular mean? It means that individual molecules are brought together by associations, molecular stickers that bring them together. And you can build up then a cluster of molecules that if the individual molecules were, say, 500,000 molecular weight, you could make a cluster that was 5 to 10 million molecular weight. And that sounded like a great recipe for achieving mist control. And because those connections are reversible, they're non-covalent. It's like stickers that are like Velcro. You can bring them together, take them apart, put them back together again. And in fact, they put themselves back together again. It's a beautiful thing. And then if the flow gets really strong, they can separate in order to survive going through a pump or a pipeline or a filter. Okay, well, it was a dead end. And I was feeling pretty guilty because I had proposed to Amaury that this was going to be the winner. And after more than 3 years of work, he had really definitive proof that this was not going to work. And in particular, because the long flexible chains, in order to do their magic, in order to stretch and retract, they can't be all clumped up on themselves. And he showed that by having stickers all along the chain, they just stuck to themselves if you put them in at low concentration. So, nobody wants to finish their PhD without having a good result. But Amaury was starting a family, and he really didn't want to make any more molecules. He said, here's the deal. He negotiates with me. I'm going to do theory to find out if it's even possible to make a molecule that would be good for mist control using a supramolecular strategy. And regardless of the answer, if it's negative or positive, I get to graduate, right, boss? I said, okay, that's fair. That's more than fair, actually. So he went and did a really beautiful little piece of theory. And he showed that it is possible, but not easy. So what he showed us was that if you wanted to have these molecules stick together and act like a very stretchy chain, you had to have the stickers at the end, not in the middle. They had to be at the end. And the best way to do it would be complementary. So a donor can attach to an acceptor, but not to itself. So he did this beautiful calculation teaching us about how these molecules would stick together. Would they make, how many unimers, how many dimers, how many trimers, all the way up into the many millions. And he showed that this little tail right there could be enough to give you a mist control effect. And you notice that this is at a molecular weight of 5 million. So it's about 30,000 backbone bonds. It's a big molecule. And when they assembled together like that, it's up in the millions. So we called them mega supramolecules. And he told us how long the individual chains had to be, what concentration they had to be, and how strongly they needed to stick together. And so, bye-bye, Henri, he graduates. And I'm feeling very confident at that point that everything's going to be great. So according to the theory, let's see if this will play. Played before. Nope, it won't. So with hand gestures. Oh, it does. Never mind. So if you imagine an equally long covalent chain, at the beginning, when you're in a flow that's elongating, they behave similarly. But something different happens once the flow gets strong enough to pull apart the Velcro. Then the two smaller parts of the supramolecule can float away and meet each other again another day and reassociate. But the covalent polymer, once you've pulled it so it breaks, it can never come back together. So if you imagine what it's like from the molecule's point of view, you're in this really intense flow, you stretch, and you let go of the Velcro, but then you end up in other parts of the flow that bring you together with other parts of chains. And if you got these sticky ends, you catch hold of each other like the Velcro. Whereas the covalent chains, they can never heal. So I thought it was a really beautiful idea. And with full confidence, I pitched the idea to a new grad student, Jeremy Way. And Jeremy was very excited about making a difference. So both he and Henri were in college when 9/11 happened. And they were both affected profoundly. So Jeremy really wanted to take this idea and build the molecules theory set and make it work. Well, when he joined, I thought it would be fairly straightforward. There were similar syntheses in the literature, but not up at the length that we needed, and maybe not with the strength of association that we needed. But, we approached it with great confidence. And then, 3 years in, we still are running into problems making the backbone of the molecules long enough. I said, Jeremy, I can't in good conscience keep you on this project. He said, just wait, boss, give me another 6 months. I'll get this. And his courage kept this project going when I was like ready to just throw in the towel. So between him and Virendra, they were able to give me enough hope to keep going. And sure enough, he succeeds. And he solves all kinds of problems, little details that you have to be a detective to find out what's going wrong in the chemistry. Because to make a really long chain, it has to be perfect. So he works it out. And then finally, 4 years into his thesis, we can do an experiment to find out if it works. And we were so excited that it does work. And so on the following video, I'm going to show you something that looks exciting on the top and extremely boring on the bottom. What I want you to remember is boring is good. So here we're looking at an experiment that was a miniature version of one that Virendra had done with big cannons. This is using actually a cigar can of fuel here and 3 propane torches continuously burning to make sure the fuel ignites. In the lower frame, those golden circles show you where ignition happened. And if we didn't have the high-speed video, thanks to the JPL camera crew, we would not have been able to tell that there was any ignition. And so here you can see that it ignites, propagates a short distance, and then puts itself out. And it wasn't really until this that I fully believed what Virendra had taught me. So everything he had said was confirmed. And the result here, if we were standing about the distance, maybe half the distance to the camera here, you could still feel the pressure pulse when the ignition happened in the untreated fuel, even though it was an amount the size of your thumb. And in the lower one, we couldn't see anything happen. We thought maybe the torches had burned out. So it wasn't until we played the high-speed video that we could see that ignition had occurred several times. So then we were super happy. And Jeremy had already shown that the polymer survives going through pumps many times and filters. And then we were actually really sad. So we saw this great result, and then we thought, uh-oh, then it won't burn in the engine. Lucky for us, the Caltech Provost Office was willing to give us funding to do an engine test. And much to our amazement, we found that it did not have a measurable effect on power or efficiency in a diesel engine. It's amazing. So it led to a startup company. So Jeremy, who, as I recall, came to Caltech to become a professor, decided he wanted to see this through. He wanted to bring this thing to market. And so he became an entrepreneur. And Simon Jones had worked in a couple of different startups, had been helping Jeremy for a couple of years. They were peas in a pod. And Jason Whaley is from the the venture capital company that supports this, Rhapsody. And so they're here in Pasadena moving this technology forward. And they've made a bunch of really wonderful discoveries since then. So it's really a beautiful story. Now let me tell you about the background. So this globe back here, that's in a building nearby, the Resnick Sustainability Institute. These guys are working on something that'll conserve energy and hopefully reduce emissions. So, you know, they're doing their part. But what about going more radical? Could mega supramolecules do something more for sustainability? And this is a story I love because it illustrates how when an older person has a lack of imagination, sometimes a younger person sees what the future could bring. So Ho-Jin Kim joined my research group, and I wanted him to work on mega supramolecules in fuel. And he's like, yeah, I don't wanna. So he helped me out. He would continue making the polymers we needed to keep that research going forward. But he said, where my heart is in water. And I'm like, oh, Ho-Jin, water's an already solved problem. He said, I don't think so. And I think that there's a lot we could do there. And even though he wasn't successful in persuading me, he stuck to his guns. And he took on what's a very difficult problem. It had taken us a few years to work out a method to synthesize the backbone that dissolves in fuel up to the length required. He said, I'm going to do that for water. And it requires a totally new kit of sticky bits. The Velcro that works in water is totally different than what works in fuel. He said, that sounds great to me. That's what I want to do. So he starts working on that, and I'm like shaking my head. Why do these young people do this stuff? And then I get a phone call from Dow. And Dow is wanting to develop more sustainable technologies for agriculture. And they need a polymer that will allow them to control mist of waterborne chemicals that are used in agriculture. I said, I've got the guy for you. And, you know, I introduced them to Ho-Jin. And Ho-Jin's kind of like, yeah, I knew, you know. And it's the most beautiful thing to be part of this, where you have, you know, on one hand, a young person who sees something you don't see. And then having circumstances allow you to see what they saw all along. And now this is supporting an effort of 3 grad students trying to figure out how we could make agriculture less dangerous for the environment. And so when you are applying chemicals, either fertilizer or pesticide, onto crops, you have a whole bunch of like shower heads. And each one is spraying out this active ingredient that you want all of it to land on the leaves and stay on the leaves. But what happens is it makes droplets of all different sizes. And the sizes that are really small, the same ones that cause the problem with the fire, they stay airborne for long distances. So you'll have these fine drops that may have a pesticide in them showing up on plants in an organic farm downwind. It's not good. The other thing that Dow taught us is that when the drop hits the leaf, the way it behaves determines how much of the active ingredient stays on the leaf versus bouncing off onto the soil. And we got really excited about the possibility that we might be able to devise a molecule that could control the way the drops behave in the shower heads and control the way they behave on the leaf. And so we're currently working on that. And it's something where I very much admire Ho-Jin Kim. And I feel so lucky to work with these people. So part of the reason I wanted to tell you this story is to show you how people from all around the world end up being brought together by circumstances that you wouldn't expect to bring them together. And I want you to know that the images that I showed of the Earth at the beginning of the talk, they were all on 9/11, the 20th anniversary of 9/11. And one of the things I'd like you to notice is this dark, dark, dark cloud over North America and kind of a stream of smoke going all the way across to Africa. That's from the fires burning in the West Pacific side of the United States and southern Canada. And so we have some big challenges ahead of us. And I would really like you, especially usually at a Watson lecture, there's some high school kids. I'd like you to consider getting to work on behalf of Earth. She needs you. There are great problems that you can solve, and in the process, you'll meet people from all over the world who also really care deeply about those problems. And things that you might think are impossible, you might be the one who makes it come true. And that's what I'd like to leave you with. And I'm really grateful that you watched tonight. I welcome your questions and comments. And this video will remain available on Caltech's YouTube channel. And you can also find other Watson lectures there. And I hope you'll join us also for the forthcoming Watson lecture as well. Good night. I'll answer questions in a moment. Excellent. So I'll pick a question from Lawrence B., who asked, did we use computational chemistry to design the molecules? And the technique that Amr used is not usually categorized as computational chemistry, but it was very much enabled by computers that allowed him to have a system of equations that described all the different possible species. So you could either have a unimer closed on itself, a dimer linear, and it went on and on and on. And he was able to solve that system of equations because of computational tools. And so in that sense, the design of the molecules that came forth was a combination of kind of pencil and paper theory and computational tools. And it's very much a credit to Amaury how he combined those to come up with the unique solution that he did. Right. So Rebecca asked, is there concern about these molecules accumulating in the environment? And so there's two types of molecules here. The ones that are used in fuel pass through the engine, and we chose a backbone structure that is chemically very, very similar to fuel. So fuel is a hydrocarbon. It has only carbon and hydrogen atoms, not only, but only trace other atoms. And they aren't completely saturated, so it has some single bonds and some double bonds. This polymer is almost exactly matched to the carbon-hydrogen ratio of the fuel. And in the emissions test, it appeared to actually reduce soot formation and to have no measurable effect on other pollutants. There was a slight increase in NOx. So the polymer is completely consumed going through the engine. The other type of polymer, so I mentioned that this was Ho-Jin's baby, that he really wanted to do this. He looked into the possible choices of water-soluble backbones, and he chose one that is currently used in agriculture. And organisms in the soil metabolize it. It's a nutrient for them. So it doesn't last very long in the soil. And he is the one who taught me all that. And then when we went to talk to Dow, I looked so smart because Ho-Jin had already understood that ahead of me. And that was also the backbone that Dow said they would like us to use. And I'm like, have I got the guy for you to meet? Here's Hojin. So I hope that answers Rebecca's question. Oh gosh. So this one might be a little bit specialized, but I hope all of you enjoy it. Nicolaus M. Hi, Julie. As a rheologist and chemical engineer, have you looked into the transient rheology of the chemistry of your supramolecules? And so we are working on that, both the dynamics of the way that they stretch using some very beautiful measurements that you can do just on a drop of fluid when it drips down and forms a thin thread of fluid, and you watch it thin to get detailed information about how these molecules stretch and resist the fluid stretching. We are interested in looking at the chemistry, but we haven't figured it out yet. So, Nicolaus, if you have a suggestion for me, please do let me know. Boy, there's some of these that I have to look up what the person's talking about. Vladimir Y asks, can these molecules be engineered to achieve higher conductivity, similar to corkscrew engineered materials? That's one where I'm going to have to look up what that material is. These current molecules are insulators, but there are backbones out there that are electrically conductive and ionically conductive. So, you know, maybe you can send me a message about what you imagine being possible with this idea. And I'll have to look up what corkscrew engineered materials are. Let's see. A live stream viewer asked about the possibilities of using these polymers in the plastic bottle industry, concerned with BPA, which is, I believe, bisphenol alcohol. And that molecule is largely, yeah, go ahead and, Jana's getting me the correct nomenclature, bisphenol A. So it's a monomer that's used in the preparation of PET. So if you look at the bottle recycle number on plastic bottles, most of the ones, for example, the ones that can handle bubbly beverages, those are made of polyethylene terephthalate. And bisphenol A is one of the compounds that's used in the synthesis, and it's largely been removed. So it's my understanding, I should look into this a bit more carefully, but after the concern about baby bottles and so on, I believe it's been largely removed from plastic bottles used for bubbly beverages. This particular polymer is not directly relevant to those bottles. The special thing about those bottles is that they crystallize, and the crystals help control their stiffness and their gas permeability. It's a long stretch from what I told you today, but we have some ideas about modifying polymers that are currently used for lower value bottles than the PET, and seeing whether or not we could make them more valuable by using these end groups to change the way they behave during processing and improve their properties. But that's a long reach from what we have in hand today. Let's see, Alex J asked, I'm curious about the considerations to ensure the fuel burn was not affected significantly in normal use. I have to tell you, Alex, I didn't think we'd get there. I did not believe we'd be able to solve that. And when we got the engine results, we were really surprised. And I got a phone call from a researcher in the Army. It turns out the Army is in charge of all food and water for all of the services across the US. And he had read in the article that we had less soot formation. And he said, you know, I really want to see how this stuff burns. And it has taken us a long time to get funding, but we now have funding in this coming year to actually watch what the polymer does to the dynamics in the engine. And one of the things, it's an early observation, so it's not really conclusive yet, but it's exciting to me, is that the conditions inside the engine have a much higher pressure than what we were looking at out on the parking lot when we did our impact experiment. Under high pressure, the way a liquid shoots into a gas is dramatically changed. And I think we'll find out that it's that difference in the physical system, the density of the gas that's interacting with the liquid, that is going to hold the clues as to how this stuff actually behaves acceptably in the engine. And I'm really excited to find out, but we don't know yet. Okay. I also can't answer the question, so that one of the live stream viewers asks, is there a residue in the engine from the burning of the polymers? That's a question that's going to require us to really, really scale up. Fluid efficiency now, they can make many kilos, I think 1,000 kilos. It's still not enough to do a jet engine test where you allow the engine to operate for thousands of hours. And that's what would be required to have a measurable deposit. So we're a long way from being able to answer that. But I'm hoping, and especially interacting maybe with the Air Force, that we might be able to have those experiments ultimately be done. And just a comment, not a question. Thank you for the shout out to high school students. I sure hope you're out there. My kid was watching with me and definitely appreciated it. So yeah, you guys are the next wave of scientists and engineers who are going to be tackling the current pressing problems that face the world. And I'm really glad that some of you are watching, and I'm hoping this helps you have the motivation to stick with STEM. I know it's hard studies in high school, but it's well worth it. Later on, you get to do work that's really exciting, really fun, and meet people from all around the world. So do stay with it. Let's see. The other two questions I can't really answer very well. Emmanuel M. asks, considering the post-9/11 context, did you consider thermite or its chemical reactions in your research? And we didn't. Feel free to send me a message with more on, what you're thinking about there. I can connect you with resources at like the National Institute of Standards and Technology that really, really looked in depth at that question. But it's outside my expertise. And then last question is from Christopher S. And also I can't really answer this one, but it's interesting. Are these molecules useful in the catalyst-assisted, sunlight-based separation of water into oxygen and hydrogen? A process recently demonstrated by Professor Domen at the University of Tokyo as a potential source for carbon-free fuel. And I don't think these polymers will be useful for that, but I do want you to know there's really exciting research underway at Caltech on sunlight to fuel. And if you send a message, I will connect you with the team of people who are working on that. And it's a really exciting area. So again, that's one for future scientists coming in. There's a lot of opportunity there, and I'd be happy to connect you with the people at Caltech who are working on that. Okay. So a new question, how much would these polymers have changed those previous disasters? This is a question of speculation, but following on the research that the National Institute of Standards and Technology did on the collapse of the Twin Towers, first and foremost, high-rise buildings are enormously safe. It is very, very hard to generate a fire that will weaken a building enough for it to collapse. It's not something you should worry about. They found that the initial conflagration of the fuel created a very high pressure pulse inside the building. It blew out hundreds of windows. And that itself allowed the fuel to burn much more completely. Normally in a high-rise fire, if only the windows on one floor broke, for example, it would not get hot enough to soften steel. So NIST had to go through layers and layers of effects that trace back to this initial burst of energy. It also stripped the insulation off of the steel. If you're in a garage and you look up at the steel I-beams and you see them coated with something that looks like I don't know, popcorn, that insulation is there to prevent radiation in the case of a fire from reaching the steel. But it was stripped off, it was scoured away. There's so much concrete flying at high velocity, hitting all those surfaces, they were scoured clean. So the initial explosion probably contributed to the temperature of the fire becoming so hot that it softened steel. It's a speculation whether or not the buildings would have been salvageable, but they might have been able to rescue everybody instead of the 2,800 mainly people trapped above, as well as the 5 firefighters down below, whose lives were lost because of the collapse of the buildings. So, and also the intensity of the heat on that day. So we don't know for sure, but I believe that the polymers might have kept the building standing long enough for everyone to get out. And you know, it's my hope that it would also help on things where you have collisions on the ground as well. And so stay tuned, you know, as fluid efficiency moves forward, scales it up, gets it out into the world, we'll find out more about what it can do. Great. So, there's a really nice comment here. So thank you for saying thank you. So at least one person felt that the lecture was interesting and understandable to non-chemists, and that was really my hope. So I hope all of you enjoyed it and found the human connection as well as the science, how they weave together. That's something I really love about this career and about Caltech. So with that, I'd like to thank you again and encourage you to stay tuned for a moment to find out about a forthcoming Watson lecture, and have a great evening.